All right, so this is how we figured out a long time ago, over 100 years ago, by the way, uh, that the Earth was billions with a B. So billions of years old means you know, it's actually 4.5 billion. So, or another way of saying that is 4.5 times 10 to the ninth years old. All right, so here's this is just one example. Okay, so I'm going to use potassium. So there's a radioactive type of potassium, potassium 40. Anyhow, it doesn't. It has a very long half life. This particular type of potassium has a half life of um, about 1.3 billion years. All right, so there it is right there. So basically, what that means, and this is true for it doesn't matter what the um, what the radioactive substance is. Um, so this happens to be potassium. Let's say you start with. I mean, this is not this is kind of a made up example, but it brings the point home. All right, so you start off with uh, a time when you have 100,000 potassium, radioactive potassium 40 atoms. All right, so that's that's just a made up number. In a rock, there's going to be trillions of these. Anyhow, um, if you wait one half life, okay, so this is literally what it means for a half life. It has to be a radioactive substance. Most potassium is not radioactive. This happens to be a radioactive isotope. That's just the same element, in this case potassium, but it has a different number of neutrons that makes it unstable. Anyhow, so one half life goes by, and half of the potassium atoms have turned into what are called daughter atoms. Okay, so daughter atoms are what the radioactive substance turns into. Okay, so in this case, the potassium 40 becomes calcium and argon. All right. So now let me just explain something that's really a really good point. Okay. So argon, right? Like if you think about these atoms, argon on Earth, um, under relatively normal conditions, is a gas. And so you don't normally find argon gas inside of rocks, right? So if you think about like when rocks formed, the rocks would solidify, um, and any gases would you know would be as the rock turns from a liquid into a solid, those gases would go off into the atmosphere. Right. So what we're saying here is after one half life, which is about 1.3 billion years, um, there's going to be now argon atoms inside of this rock. And in fact, because we know the decay of this particular type of potassium, we know that there's after one half life there should be this many, 5,000. If you started with this many radioactive potassium atoms, you'd have half of them would still be potassium. Um, about um, 45,000 would be calcium, and then 5,000 would be argon. All right, so then another half life goes by. So now two half lives have gone by, and you've reduced the number of potassium atoms by half, and of course you've gained twice as many calcium, and of course, well, I'm sorry, not twice as many. Yeah, because this is half life. So you get half of these, all right, and then the same ratio of what was left, right? So you started with the in this case going from this half-life to this half-life, you started with 50,000 potassium, and so you've added, you know, what would that be? 55% more. Okay, so that's where these numbers come from. I mean, at any rate, as time goes on, so this is 1.3 billion years, another 1.3 billion years, another 1.3 billion years, and another 1.3 billion years. So, for example, you would find if you started with this many radioactive potassium atoms, so let's see, how many half-lives? 1, 2, 3, 4 half-lives have gone by, then you should see almost, 9,375 argon atoms. Of course, the Earth is not that old, so you don't, remember, this is a made-up example, so you never start with exactly 100,000 potassium atoms. It doesn't work like that. And so what we'll do is, this, you don't know how many potassium atoms you started with, okay? But you can assume that there were no argon atoms in the rock. When the rock solidified, there were no argon atoms. The argon comes from radioactive decay, all right? And so that's the only way that the argon gets in there. And so you basically look at the ratios of potassium to argon, potassium to calcium, and you can say how many half-lives have gone by. Now, I know it's not going to be like, as this thing indicates, this is very artificial, 1, 2, 3, 4 half-lives. That could not have taken place because, the Earth simply isn't that old, right? Much more likely that, you would find this number or somewhere in between these. All right. So anyhow, that's how we tell. All right. So another way of doing it is with a different isotope. This one you've probably heard of, uranium-238. So it turns out that uranium-238 eventually, so there's lots of daughter atoms because the stuff that uranium-238 becomes is also radioactive until it becomes lead. And it's a particular type of lead. It's called lead-206. And so lead is actually a really good example. All right, so as I was saying, with lead, with uranium-238, when one half-life has gone by, the uranium-238, half of it is gone, just like this situation, right? Half of the uranium-238 would be gone. But see, the nice thing about uranium-238 is it just becomes lead-206, right? It does. There are steps before it gets to lead-206, but those steps don't last for very long. And so when you're talking about billions of years that have gone by, all of the uranium-238 has become lead-206. Okay, so none of the other daughter atoms are there. And of course, lead-206 is very stable. All right, so you take a rock, from the Earth, a really old rock, and this is part of the challenge, is because a lot of the rocks that you find, common rocks, around are not very old. They're billions. Some of them are billions of years old. Some of them, the ones near volcanoes are not that old. But if you find a rock that is particularly old, and there are certain places on Earth where you can find these rocks, you do a uranium-238 test, and you find that. Here's the situation, right? If one half-life has gone by, half of there's 50. So think of it in terms of percentages, right? 50% of the uranium atoms that are found in the rock are uranium-238, and then 50% of them are lead-206. Right? The only way for that to happen is if one half-life goes by. Right? So you might say, all right, well, wait a second. What if the lead-206 just happened to be there when that particular rock was found? And that's a completely valid point, right? That what if the lead was there, right? And if you took one sample in one situation, where you found this one rock, and half of it was uranium, half of it was lead. Not all of the rock, right? Just the amount of lead there was 50% of what the amount of uranium that was there. Half of it was lead, and half of it was uranium. In that one instance, you couldn't really say anything about the age of the Earth. Okay, so now I want everybody to understand this. It's really a really important point. So every time we find rocks with uranium-238 in them, right? Every single time, all over the planet Earth, not just the planet Earth, on the moon, and the rocks that sometimes we have meteors that fall to Earth. So these are rocks from other parts of the solar system. So every single time, the oldest rocks that we ever find, half of the uranium has turned in, half the uranium-238 has become lead-206, and it's always a 50% ratio, right? Half of it is lead-206, half of it is uranium-238, and the only way for that to happen is if one half-life of uranium-238 has gone by, and that's exactly what we find, right? That's 4.5 billion years, right? So, I mean, this is just another way of doing the same thing, but you got several half-lives that go by, and so you got these other ratios because you have different daughter atoms to consider. With uranium-235, I'm sorry, I didn't mean to say 230. The uranium-238, the most common isotope of uranium, it always becomes lead-206, and if enough time has gone by, and we always find the ratio half and half. I mean, like the thousands upon thousands, hundreds of thousands of times we have looked and counted, we always get that ratio of half lead. I'm pointing to potassium here, but half lead and half uranium-238, right? So never ever do we find more lead or less lead. Every time we find uranium-238, it's always the same ratio, right? And that is overwhelmingly convincing that the Earth is 4.5 billion years old. And this same thing goes with these other. You have to have something with a long half-life, like potassium, right? The potassium-40. That's another one. And they all agree, like they all give you the same 4.5 billion years. That's the age of the Earth. All right. So anyhow, that's how we figured out, and that's how we do the radioactive dating with other rocks that we find. Mostly it's stuff that has arrived from space. These meteors hit the atmosphere, and some of them burn up, and there's nothing left. But some of them will actually reach the ground, and then you study them, and you never find anything older than 4.5 billion years because, right, that's the age of the solar system. That's when our sun was formed, right? And that's when all these, all of these, the original amounts were there 4.5 billion years ago, whether it was uranium or potassium or any of the different radioactive elements. I'm just giving you two examples. All right, so that's how it goes. Okay, so there's the 4.5 billion years. yeah, I mean, this is